Welcome back. In this lecture, we are going to cover the atmosphere. Atmospheric science is an extremely rich field, and unfortunately we only have one lecture devoted to it. So we're going to focus on the atmosphere's vertical structure, adiabatic lapse rate, and the greenhouse effect. But the lectures dealing with general circulation also have a lot of topics related to the atmosphere, so you will get to revisit and build on these topics. Let's get started. First off, I cannot express enough how crucial the atmosphere is to life. I'm sure you're all pretty familiar with some basics of the atmosphere. It contains gases that we need to breathe in order to stay alive. But there are actually a lot of layers to it, and it has changed over geologic time as well. The atmosphere is kind of analogous to a cellular membrane. It is quite thin, and it regulates what can enter, for example it filters UV rays, and what can exit, like infrared radiation. Humans live at the atmosphere's bottom. Living organisms continually exchange gases with the atmosphere. For example, photosynthesis takes in CO2 and puts out oxygen, while respiration does the opposite. But what is the atmosphere? An atmosphere is the envelope of gases that surround a planet, and it is retained by the planet's gravity. There are many layers to Earth's atmosphere. The troposphere is what we interact with. Above the troposphere is the stratosphere, followed by the mesosphere, the thermosphere, and finally the exosphere. I think it is important to put into context how much atmosphere there is on Earth. The total mass of the atmosphere is 5 times 10 to the 18th, or 5 quintillion kilograms, most of it in the lower portions. Now the volume of the atmosphere is 3.9 times 10 to the 15th cubic meters, and the number of molecules in the atmosphere is 1 times 10 to the 44. But how thick is the atmosphere? The atmosphere is incredibly thin on planetary scales. If Earth were the size of a 12-inch globe, 99% of its atmosphere would be about as thick as the paint on that globe. Here's a really cool image of the different layers of the atmosphere from the International Space Station. You can really see clearly the troposphere versus the stratosphere versus the upper regions of the atmosphere. Then you can clearly see when there is no longer any atmosphere at all in outer space. We're going to talk about some gases, so let's take a step back and cover chemical elements, atoms, and molecules. Visible matter is composed of atoms. Atoms are composed of protons, neutrons, and electrons. The number of protons in an atomic nucleus determines the chemical identity of that atom. That is, what chemical element it is. A chemical element is a substance composed of only one kind of atom. The periodic table of elements has a list of all known elements. Elements can be bonded together to form many other substances. These are molecules or ionic crystals. Water, H2O, and carbon dioxide, CO2, are relatively simple molecules that are important for climate and life. DNA is a very complex large molecule made of carbon, hydrogen, nitrogen, oxygen, and phosphorus. But what gases make up the atmosphere? Well, 78% of the atmosphere is made up of dinitrogen, or just nitrogen gas. This molecule is fairly inert because of the triple bond that binds the two nitrogen atoms together. Then about 21% of the atmosphere is O2 or oxygen, while about 0.04% is CO2 or carbon dioxide. Lastly, 0.96% of the atmosphere consists of other gases. Most of this is argon, which is a noble gas and inert. Well, that's the breakdown for Earth. Of course, Earth is not the only planet to have an atmosphere, and the types of gases vary depending on the planet in question. Both Venus and Mars have much higher percentages of CO2 than Earth, but the atmospheric pressures vary, and so the density of gas molecules are different. For example, Mars's current atmospheric pressure is tiny compared to Earth's. Venus's atmosphere is quite unique because it has sulfuric acid clouds in its atmosphere as well. So the important thing to remember is that Earth isn't unique in terms of having an atmosphere, but our atmosphere is very different from nearby planets that also have atmospheres. And Earth's atmosphere allows life to exist on it. Earth's atmosphere hasn't always looked like it does today, though. Early Earth didn't have any oxygen in it at all. The gases that were present were those that were outgassed due to increased volcanic activity during the Hadean. That was the geologic eon when Earth looked like a hellscape, like Hades. It took quite a while after photosynthesis evolved for oxygen to build up in the atmosphere, and so early life forms didn't cycle oxygen and CO2 back and forth like they do today. Additionally, it took a while for nitrogen gas to be the dominant gas in the atmosphere, and early Earth had much higher concentrations of potent greenhouse gases that make up a much smaller fraction of our atmosphere today, including methane, water vapor, and carbon dioxide. Atmospheric pressure is the force per unit area exerted by the atmosphere due to the air above a given location due to its weight. It is literally the weight of the overlying air. Because of that, atmospheric pressure is not uniform with altitude. Typical units are millibars, hectopascals, atmospheres, or inches of mercury. At sea level, the atmospheric pressure is 1,013 millibars, 1,013 hectopascals, 1 atmosphere, or 30 inches of mercury. The fact that air pressure changes with altitude is probably something that you have experienced before with plastic bottles. These bottles were emptied and closed at about 3,000 meters above sea level in the Sierra Nevada. Then they were brought down to near sea level. That means they went from about 700 millibars of pressure to about 1,000 millibars of air pressure, since air pressure increases the closer you are to sea level. That's a huge air pressure difference between inside and outside the bottles, and the bottles are being squeezed as a result. Here's a great image that shows how temperature varies with altitude. You can see that temperature actually increases or decreases with increasing height depending on what layer you are in. It is variable. Within the troposphere, the portion of the atmosphere we directly interact with, temperature decreases linearly with increasing altitude above sea level. Hence, it's cold in the mountains. Even though temperature increases with altitude beyond the troposphere, it feels colder because air pressure continually decreases with increasing altitude. Now that we have talked about the vertical structuring of the atmosphere with regard to pressure and temperature, let's talk about the adiabatic lapse rate, because that affects the temperature of an air parcel. The adiabatic lapse rate is the rate at which the temperature of an air parcel changes in response to the compression or expansion associated with elevation change, under the assumption that the process is adiabatic, which means that no heat exchange occurs between the given air parcel and its surroundings. Rising air is exposed to lower and lower pressures, and so it expands and it cools. Things that can cause air to rise include temperature. Hot air will naturally rise because it is less dense, or when wind blows over a mountain range, forcing it up and over the mountaintop. The flip side of this is that descending air is compressed and warms up. The Santa Ana winds are a really good example of this. The image with the blue and red arrows shows this effect really well. Then the image on the far right shows a linear relationship between altitude and temperature within the troposphere. The adiabatic lapse rate also affects rainfall. This is because cooler air has less capacity to hold water. Ascending moist air cools and condenses, causing rainfall. Dry descending air warms up, increasing its ability to hold water vapor and promotes evaporation. This will happen anywhere air ascends or descends, but is particularly visible on mountains. This is known as the rain shadow effect. I have a really helpful diagram that shows the rain shadow effect on the right, and then an aerial view of Washington State. The rain shadow effect causes dense vegetation on the ocean-influenced windward slope, where lots of rain occurs, then deserts on the dry leeward side. The next topic that we are going to cover is greenhouse gases. Water and CO2, and some other greenhouse gases, also known as GHGs, are transparent to incoming or shortwave radiation, but absorb infrared or longwave radiation emitted by the Earth. Greenhouse gases re-emit infrared radiation, with some going back down to reheat the Earth and lower atmosphere a second time. This is known as the greenhouse effect because it is analogous to a seemingly transparent greenhouse keeping heat in. These are the really important greenhouse gases to the Earth system. Carbon dioxide and methane are the greenhouse gases we hear most about. Nitrous oxide, also known as laughing gas, is also a greenhouse gas. And a lot of people don't realize that water vapor is also a greenhouse gas. Greenhouse gases work, meaning they cause a greenhouse effect, by absorbing infrared radiation. The infrared radiation strikes a molecule, like carbon dioxide, and causes the bonds to bend and vibrate. The image on the far right shows different types of bending and vibration. Each greenhouse gas molecule has its own absorption spectrum, which is the range of energy it is opaque to and absorbs. That is what the image on the left is showing. It shows the wavelengths of radiation that each greenhouse gas absorbs. The greenhouse effect is natural and actually keeps Earth habitable. It keeps the Earth about 33 degrees Celsius warmer than it would be otherwise. But by adding CO2 to the atmosphere, humans are making it more opaque to infrared radiation, meaning we are causing it to absorb more of the outgoing infrared radiation. This is causing increased warming, and this is known as anthropogenic global warming or anthropogenic climate change. Anthropogenic just means human-caused. The image is showing global average temperature change over the last 2,000 years. You can see that global temperatures started to increase with the Industrial Revolution, when humans started to emit significant amounts of CO2 by burning fossil fuels. Recall that water is also a greenhouse gas. It actually participates in a positive feedback on Earth, but it needs something else to cause the initial change. That means that water vapor isn't going to precipitate a change, it will only reinforce the change that is already happening. Another way of saying that is that water vapor doesn't currently control Earth's temperature. Earth's temperature controls the amount of water vapor. Remember that warm air can hold more water vapor. So if a volume of air contains its maximum amount of water vapor, and then the temperature is decreased, some of the water vapor will condense to form liquid water, causing rain. That means there will be less water vapor, which is a greenhouse gas, in the atmosphere, and cooling will be reinforced. The opposite is also true. If the temperature of an air parcel increases, then more water will evaporate, meaning that there will be more water vapor, a greenhouse gas, in the atmosphere, and warming will be reinforced. The decrease in temperature with height in the troposphere, which is due to the adiabatic lapse rate, is actually fundamental to climate, life, and the way our planet operates. For one, the lapse rate controls or maintains the surface temperature, and thus the strength of the greenhouse effect. The adiabatic lapse rate is also essential to cloud and rain formation, due to cooling of rising moist air, which leads to water vapor condensing out as rain. So cooling temperatures in the troposphere essentially act as a cold trap for water. This is essential to the hydrologic cycle, which we will learn about in another lecture. It also protects Earth from losing water to space by keeping water in the oceans and the troposphere. The upper atmosphere is actually very, very dry. The atmosphere protects the ocean and allows it to exist as liquid. Substances, including water, have three phases: solid, liquid, and gas. The state depends on the temperature and pressure. The atmosphere on Earth allows for a liquid ocean to exist by providing the right pressure and temperature via the greenhouse effect. We have had liquid oceans on this planet for about 4 billion years, and this has allowed life to evolve. Another important aspect of the atmosphere that we have to cover is the ozone layer. Ozone in the stratosphere is important for life as it absorbs harmful UV rays from the sun. UV radiation destroys DNA. There is an ozone layer in the lower stratosphere that allowed life to evolve on land. Ozone near the surface, which is called tropospheric ozone, is a harmful air pollutant. It is a free radical and damages DNA, so it's bad for us to directly interact with. But up high in the stratosphere, it protects us. Ozone is formed by oxygen in the stratosphere, which migrates up from the troposphere. So certain types of life, particularly photosynthesizers, made a layer in the stratosphere that protects other life. The image on the right shows the process of the formation of ozone, if you're curious. The last topic we are going to cover in this lecture has to do with the atmosphere and the magnetosphere. The magnetosphere is contained within the Earth's thermosphere. The magnetosphere is the region where the Earth's magnetic field, which extends into space, interacts with the charged particles coming from solar wind. Earth's magnetosphere is a vast comet-shaped bubble, which has played a crucial role in our planet's habitability by protecting life from harmful solar wind and cosmic rays. It also creates the aurora borealis, which is also known as the northern lights. The stream of particles interacts with gases in the magnetic field, the magnetosphere, generating magnetic auroras. Earth's magnetic field spans across thousands of kilometers in space. As a rule, the more active the sun is, the more stunning the auroras will appear on Earth. That concludes the material for this lecture. Let's go through and review the main points. The atmosphere is essential for life in many ways. The adiabatic lapse rate is the decrease in temperature with rising altitude above sea level within the troposphere because of decreased atmospheric pressure. The atmosphere is transparent to visible light but semi-transparent to infrared radiation, causing a greenhouse effect, which causes the Earth and lower atmosphere to be reheated. The greenhouse effect makes the Earth habitable, but humans are causing excessive warming through the production of greenhouse gases. The lapse rate also affects the strength of human-caused global warming, allows for clouds and rain, and protects Earth's water and oceans via a cold trap. The atmosphere's pressure and temperature also protects the oceans. The ozone layer in the atmosphere protects the Earth from harmful UV radiation. The atmosphere and Earth's magnetic field protect life from harmful solar wind and cosmic rays. Thanks for sitting through the lecture. To test your learning, I suggest you review the material and make sure you can complete these exercises.